Welcome to Lecture 21. We have two topics left. That is energy and gas laws, behavior of gases. We are going to talk about energy briefly today as it pertains to changes in chemical reactions and also just changes in energy when one form of energy is transferred to another, but specifically transfers of heat. And then we're going to finish up today's lecture by just getting you started on thinking about gases, just some few basic particle properties, and then we'll begin the gas laws in the next lecture and conclude them in the last. All right, energy. And we're going to talk about the difference between heat and energy. Oh, I'm sorry, well, heat is energy, but the difference specifically between energy and temperature. All right. Scroll down a little bit. We got some definitions and some things to think about. Energy is basically the capacity to do work or produce heat. Heat being a byproduct of many energy changes. Some units of energy are the horsepower, calorie, and the one that we're going to use will be the joule. We've used that, I think, before in a couple of instances. And we're going to continue to use that as the metric system unit for energy. Heat is a form of energy that is harder to turn into work. It's kind of, a lot of scientists and engineers look at heat as wasted energy because it's so hard to harness it and get useful work out of it. However, heat is defined as the energy that is transferred from a hot object to a cooler one, never the reverse. Now, what I usually do with students is illustrate the difference between temperature and energy is I have a beaker of boiling water going in the lab or the classroom, and I ask for a student volunteer to have some of that boiling water, out of a dropper, dropped onto the student's hand. Generally, I get one or two volunteers, and they let me drop a few drops of boiling water on their hand. Now, of course, what I ask the group before I do that is, would you agree that if I do this transfer quickly enough that the temperature of the few drops of water in the dropper is the same as the boiling water in the beaker? And generally, I can get students to agree to that. And then I ask this student, the volunteer, whether or not they're willing for me to pour the whole beaker of boiling water on their hand. And that demonstration is the difference between heat and temperature. And you intuitively know that there is more heat in that beaker full of boiling water than there was in the dropper, even though technically they're at the same temperature. The amount of water affects the property or the entity that we refer to as heat. So temperature is the measure of the average kinetic energy of particles. The temperature scale that measures that most closely, that speed of particles, is the Kelvin scale. And that's a different one than we have used before. So as we get into gas laws, we're always going to be using the Kelvin scale. And you might have heard of absolute zero, and that is negative 273 degrees Celsius or 0 degrees K, 0 degrees Kelvin. Interestingly, we don't use the little degree symbol when we are talking about kelvins. The important thing in any energy transfer is that we don't lose any or create any new energy, and that is referred to as the law of conservation of energy. All right, so how do we go back and forth? Let's talk about that temperature scale just a little bit. Your book, very much like other textbooks, has lots of problems on going back and forth between Celsius and Fahrenheit. Don't know why, since Fahrenheit is not used in science. So we generally use the Celsius scale, but if we are talking about this subject and especially the gas laws, we are going to be using the Kelvin scale. And we go back and forth between Kelvin and Celsius by adding 273 to the Celsius temperature, or if we have to do it the other way, The Kelvin temperature minus 273.15 to be exact is the degrees Celsius. I probably will assign one problem in the recitation going back and forth between Celsius and Fahrenheit. As an American, we still use the Fahrenheit scale here. Am perfectly comfortable using the Fahrenheit scale at home and the Celsius scale in the lab. There are two basic forms of energy which you've probably learned in the past, and that is kinetic energy and potential energy. When energy is transformed, for instance, going from electrical to electrical, from chemical, and so on, you are turning potential into kinetic and vice versa. We do this in chemical reactions as well, and I have a very funny, but I think very easy to understand little demo or little animation that shows this relationship between potential and kinetic energy as it pertains to molecules. So I'm going to go ahead and open up Firefox, and we're going to look at that, because what we're going to be talking about as we get into talking about chemical reactions is the changes in energy associated with chemical reactions, and it's all about making and breaking bonds. All right. I think I did that right, so let me get rid of this first part. All right, here we go. So this is a little demo about how energy is both transferred back and forth between kinetic and potential. So here we are. All right, let's watch that one more time. So in the first part, we are breaking a bond, so energy has to be added. When we make a bond, energy is released. So one more time. When you break a bond, you are pushing the ball up the hill, adding energy in, and we're going to look at this graphical representation in a moment. One more time. So as we break the bond, we have to put energy in. So you have to push the energy ball up the hill, and then when we make a bond, we release energy, or energy flows downhill in the negative direction. So that's just an illustration of how kinetic and potential energy are, when you're at the top of the curve, you have high potential energy. Of course, when it rolls down, you are transferring that potential energy into kinetic energy. And then you get to the bottom of the hill. Then in order to do the reverse, you have to push up the hill, which is kinetic energy. And then when you get to the top of the hill, you've transferred it back to potential energy, and so on. So just a little physics talking about there in terms of energy. So every time we do a chemical reaction, you always have this balance between breaking and making bonds. All right, so when a molecule forms, potential energy drops. So that is the ball falling down the hill. This is the only reason that molecules really do form, is that you lower the system in energy. So when we do chemical reactions, we break bonds, which is putting energy in, and then when we make bonds, we take energy comes out. So once the bonds break, so let me just write it here. So breaking bonds, and we're going to go over this again in just a minute. Breaking energy in, and then making bonds, energy out. So breaking bonds, that happens on the reactant side. Making bonds, energy out, happens on the product side. So you always have this energy in, energy out going on in chemical reactions. However, before we started studying chemical reactions, physicists and scientists were studying about transferring energy back and forth in a subject that is called calorimetry, where you measure differences in temperature for different types of processes and so on. It's still about particles, but there really are no chemical formulas. So this is a really important statement right here. Unlike temperature, which we can measure, we cannot directly measure energy or heat. What we talked about just a moment ago, the energy that we have to put in to break bonds and the energy we get out when we make bonds, we can't directly measure that either. What we can do is measure the difference between them and get some idea as to what is going on. So we have two different symbols for heat. Remember, heat is energy. Q, which we're going to use when we talk about calorimetry, so no chemical reaction. Okay. I'll qualify that in just a moment. And then H, when we are talking about chemical reactions, and we call this enthalpy. And we never just say H, we always use this triangle, which means the triangle, you'll see lots of them in this subject, especially when you get to 131, because we really are just touching on it in this lecture today. This means change. Okay, we're going to see it a little bit today, but as you study this in more detail in 131, you're going to see lots of triangles, and it means change. All right, so Q, when we're talking about calorimetry, measuring differences in heat, and H, when we're talking about chemical reactions. Now, we often combine the two. When I want to know the enthalpy for a chemical reaction, we will take the energy change for the chemical reaction and transfer it to something like water, and then we are using calorimetry to measure the enthalpy of the chemical reaction. So I'm sure that just made sense. So let's talk a little bit about what changes in heat without a chemical reaction are dependent upon. Okay, so there are three things: the nature of the substance. So let me ask you this before we leave this nature of the substance. Which kind of chair would you like to sit in on a hot summer day if given the choice between a plastic chair and a metal chair? Well, of course you're going to pick the plastic chair because you know intuitively that the nature of plastic is that it doesn't heat up as fast as metal does. So nature of the substance depends on the material it's made of, which of course depends on those particles. All right. 2, the amount of substance. Remember my boiling beaker of water, boiling water in a beaker and dropping it onto a student's hand. Certainly the amount of substance matters. And 3, its temperature. So dropping a few drops of boiling water is one thing, dropping a few drops of room temperature water, the student would be fine with me pouring the whole beaker full of room temperature water on their hand. The amount of heat in those is dependent on what temperature it is. Okay. Now, how do we quantify this? Depends on material. Well, it just so happens that there is a constant for materials, which is called either the specific heat capacity or just specific heat, and is the amount of energy, heat, needed to raise the temperature of 1 gram of a substance 1 degree Celsius. And that definition is right here. The amount of heat needed to raise 1 gram of a substance 1 degree Celsius. And of course it's different for plastic than it is for copper or iron or a metal like those. And it's usually measured under constant pressure conditions, so it gets the symbol CP. So if we were talking about calorimetry, remember we're going to use the symbol Q, and Q is measured in joules. So if I have a chemical equation, then my units have to be the same on both sides. So let's see how that works after I answer the phone. Sorry about the interruption. That was my daughter who is obsessing over hearing about graduate school. Okay, back to our little equation here. All right, let me remind you that this Q equation is for when there is no chemical reaction. Okay, so I'm going to write that off to the side. No chemical reaction. Even though we can use this to find heats of a chemical reaction in the lab, generally in terms of problem solving, you have no chemical reaction. Okay, so back to these units. Of course, if one side is joules, that's what Q is measured in because it's energy, then the other side has to also come out to joules. So mass, of course, is measured. This is our amount, number 2 up here in our little 3 things. So amount is mass, and that's in grams. Okay. Remember, our triangle means change, so this is the temperature change, so that's our number 3 up here in our 3 things that affect the amount of heat. And we are always going to get the change in temperature by doing the final temperature minus the initial temperature. And there's a reason why. We'll talk about that in a moment. And then here is that, and that's measured in degrees Celsius or Kelvin. And then C, the specific heat, is measured in joules, there's the joules, per gram degree Celsius. So when you multiply the 3 things together, the grams cancel and the degrees Celsius cancel, and that's how we end up with joules. Okay? All right, back to why we do TF minus TI, final minus initial. If we go down in temperature, then my final temperature is smaller than my initial, and I will end up with a negative Q. Negative Q implies that heat has been given off, and we have a term for that. We call it exothermic. So we went down in energy, we went downhill in the negative direction. A positive Q means that energy went in uphill, and that's called endothermic. So the sign will tell us what happened to the energy. Okay, so this is used to calculate heats of reaction. Like if you wanted to burn marshmallows or nuts, you could transfer that energy. When you have no chemical equation to write, you can transfer that energy to water, usually is how it's done, measure the change in energy for the water, and because of the law of conservation of mass, the Q of the reaction will be opposite in sign to the Q of the water. So that's what's usually done in the lab. So we could even have a chemical equation, and we're trying to find its heat, and we do it using this technique. All right, so the Q equation, and we're going to work examples where we apply that. Okay, I'm going to scroll. Now, if we are talking about chemical equations, then we can calculate heats of reaction from other kinds of data, and you'll do that in 131. So let's review what we know and introduce and talk about these terms a little bit more. When reactants react to form products, bonds are broken, and we know that we have to put energy in to do that, endothermic, and then new bonds are formed, and that is exothermic because energy is given off going downhill. And we know that the reason that happens is because the only reason that bonds form is to take these substances involved to a lower energy state. So when we are going down the hill, okay, we are locking that potential energy back up into the bonds so that it can be then, we can go back and forth up and down the hill, potential to kinetic, and vice versa. So in every chemical reaction, we have the endothermic, the bond breaking, and the exothermic, the bond making. The balance between the two dictates whether a chemical reaction is overall exothermic, which means that the bond forming step is bigger, or endothermic when the bond breaking step is bigger. All right, so if a reaction is endothermic, then enthalpy can be thought of as entering the reaction on the reactant side, and if it's exothermic, heat can be thought of as exiting the reaction on the product side. So if I look at these two chemical reactions, I see the energy written into the chemical equation. That is one way of obtaining enthalpies for a chemical reaction. There are several ways to do it, okay? Well, it's the side it's on that tells me whether it's endo or exo. So in this first example, the heat is written on the product side, so this one is exothermic. It's exiting the reaction. So it's the side it's written on that tells us. This one, the energy is entering the reaction, so this one is endothermic. Now when I write chemical reactions, I never write A plus B goes to C minus D. We never see a negative. If I were to take now we've just said that if something is exothermic, then that means that the bond forming step is bigger, and it would actually be negative. All right, so if I take the enthalpy out of the equation, then I would write it this way, and it would be another way of showing that information, the heat for the reaction. So I can write it in to the reaction, or I can write it separately. For this first reaction, I would write delta H of reaction equals minus 393.5. So that's why I said we don't, because it's exothermic, it's negative. All exothermic heats are negative because you're going down in energy overall. So we don't say carbon plus oxygen goes to CO2 minus 393.5. If it's written into the reaction like it is up here, then it's the side it's written on that tells us whether it's endo or exo. If it's written separately from the chemical reaction, it's the sign that tells us whether it's endo or exo. Negative is exothermic. So in the case of this second reaction, I would write heat of reaction is equal to 285.8. Sometimes we put the positive, sometimes we don't, of kilojoules. And it's the sign that tells me it's endo. Forgot to put my kilojoules. Okay, so it's joules, but it's kilojoules, so it's 1,000 joules. All right, so written in, it's the side. Written apart from the chemical equation, it is the sign. One more thing before we leave this topic. Let me rewrite that second equation. This equation, any thermochemical equation, and that's what we call these because not only is it a chemical equation, but it also contains thermo or heat information. This amount of energy that's written into the reaction, or even if it were written separately, it's for this reaction as written. That means it's for 1 mole of water, making 1 mole of hydrogen and half a mole of oxygen. So I can certainly change those amounts, and I would know exactly how much heat would have to be put into this reaction if I change the amount. So for instance, this is the amount of heat for 1 mole of water. All right, we're going to do a little direct proportion. How much heat is it for 2 moles of water? Okay, so I can change this to, any amount, and if 1 mole of water, okay, for 2 moles of water, and then I solve for x. This is the amount of heat for half a mole of oxygen. How much heat would it be if we gave off 10 moles of oxygen? I solve for x. So when you set up a direct proportion, as we have done in other topics in this course, it doesn't matter what's on top, what's on the bottom, as long as the two sides agree. It's just a handy little mathematical technique for comparing amounts. Okay, and another way, one more way of showing heats of reaction is to do it graphically. So I've already shown you the little simulation with the ball rolling up and down the hill. Well, you can certainly think of it this, these graphs, I think, become maybe a little easier to understand having seen that. So if something is endothermic, that means we push the ball up the hill in the positive direction of energy. We had to put energy in, okay? So endothermic reactions, the reactants start out at a lower energy than the products do. So you're going in the positive direction. No matter what your energy curve looks like, the enthalpy for the reaction is, as it's shown here, the difference in energy between the products and reactants. Okay? So that's an endothermic reaction. An exothermic reaction would be opposite. Energy flowed down in the negative direction. So, hold on, let me get rid of that little. Okay. Energy flowed in the negative direction. So products are at a lower energy than the reactants. So exothermic, negative, energy is going in the negative direction. All right. When you get to 132 and 131 and 132, you may see energy curves that look a little bit more complex. Now, when you do start to see those, remember that the change in energy, or the heat of the reaction, the enthalpy of the reaction, is the difference between the products and reactants. No matter how big or small or so on, you might even have several humps, okay, in your energy curve. And these represent just something else to consider in terms of reactions, and it's very important. We're just not going to spend any time doing it. So you could have a double hump up here, and that means different things, but the change in energy for the reaction is still the difference between the reactants and the products. So this reaction here represents another exothermic reaction because the products are at a lower energy than the reactants. Okay? You can think of the x-axis as being time. And this energy of activation is the amount of energy, the hump you have to get over before the reaction can happen. And you will talk about that in probably 132. Okay, so 3 different ways we can talk about energy of a reaction. We can write it into an equation, we can look at the sign, or we can look at one of these graphs. And that brings us to our practice. And then we're going to finish this lecture up by talking about properties of gases. All right, so determining, if you're thinking about everyday processes and you're trying to decide whether energy came out or energy went in, this is the way to think about it, especially if you're talking about phase changes and things like that. Endothermic, energy going in, particles speed up. So that's another way to think about it. So if you're talking about a phase change, if you have to speed the particles up, it's endothermic. If you are slowing them down, or you want to slow them down, or need to slow them down, then you have to get rid of some energy to do that, and that would be exothermic. So if we are going from a solid to a gas, are we speeding the particles up or are we slowing them down? We're speeding them up. So this is endo. So I'm going to put the sign, okay? I'll indicate the sign of delta H. So it would be positive for dry ice subliming. So yes, we can talk about the enthalpy of a phase change, and you will when you get into either 131 or 132. And you'll talk about things like heats of fusion, and if it's about this 1A, it will be a heat of sublimation, and so on. All right, so there are enthalpies, of course, so they're always got a triangle in front because we can't measure it directly, but we can measure the change. But if I'm going from a solid to a gas, I am speeding the particles up, so that would represent an endothermic change. The wax in a candle burning. Am I giving energy off? Yes, I am. So this should be negative. That's the chemical reaction part of a candle burning. But there's also a phase change part of a candle burning, and that is the wax that melts from the burning. And that's just a phase change, a physical change. So is melting represented by particles slowing down or speeding up? They are speeding up, so that part would be positive, endothermic. All right, number 2, perform each temperature conversion. So we're going to go grab those temperature conversions, especially for Fahrenheit to Celsius, and we'll work through these together. So let me scroll back up because I don't have them memorized. All right, and let's take these and bring them down. Oops, too far. All right, we'll put them right here. Okay, so if I'm going from Fahrenheit to Celsius, then I need to use the middle one here. Okay, so I'm going to take degrees Celsius equals 102 minus 32, and then divide it by 1.8. Okay, so putting that in on my calculator. Turn the light on. I'm sitting here in the dark. And I get 38.9 as my Celsius temperature. Okay. Going from 0K to Fahrenheit. Now up here there is no direct conversion from Kelvin to Fahrenheit, so we'll have to do it from Kelvin to Celsius and then from Celsius to Fahrenheit. So in order to go to Celsius from Kelvin, I am going to take 0 minus 273.15. So that is negative 273.15 degrees Celsius. And then I will plug it into the Fahrenheit equation here. So 1.8 times negative 273.15. So absolute zero is 0K, which is minus 273.15 in degrees Celsius. And we're about to see what that is equal to in degrees Fahrenheit. So why is that important? Well, scientists used to say that all particle motion would stop at 0 degrees Kelvin. Well, they have changed their tune on that because we have gotten very close to absolute zero, and we have found that that is not absolutely correct. And I get 523.7 degrees negative 523.7 degrees Fahrenheit. Okay. C, going from Celsius to Fahrenheit, so we just did that one. So 1.8 times the negative 48 plus 32. Oh, I think I just messed up on the B. Let me redo that. So 48 times 1.8, and that's a neg.
Okay, whatever.
All right, so the 1.8 times 48 is negative 86.4 plus 32. That's where I messed up earlier on this one. So I need to redo that. Okay. And then I end up with 54.4, negative 54.4 for C. Let's go back to B, and let me do that again. And so I was wrong there. It should be, of course it's still negative, 459, negative 459.7 degrees Fahrenheit. Okay, one more. 273K to Celsius. So I'm going to take the 273 minus 273. So that would be 0 degrees Celsius, and I'm just going to ignore the 0.15. I guess I could put the 0.15 on, and then that would be 0. So if I did that, then it would be negative 0.15 degrees Celsius for D. All right, so this is just manipulating these equations. I'm pretty confident that you would be able to do that. All right, number 3. Calculate the amount of heat required to heat a 3.5 kilogram gold bar from 21 to 67 degrees. So I see a mass in number 3, and I see a temperature change, and I see a specific substance that I could look up a specific heat for. And I'm going to grab a book and tell you which page that information is located on. Okay, this little topic about energy change is actually located in chapter 3. And on page 74 in your textbook, you will find different specific heats for different substances. So we are going to be using the Q equation here. And we're going to plug in everything that we need to solve for heat or Q. So Q is equal to mass, and we're going to change this to grams. So 3,500 grams times specific heat of gold, and on page 74 it is listed as 0.128 joules per gram degree Celsius times final minus initial for our temperature, so 67 minus 21. And I get 46 degrees Celsius. Okay, so those cancel and the grams cancel, and I'll end up with my joules. So times 3,500 times 0.128. And I end up with 20,000, or 2.06 times 10 to the 4th joules, which is 20,608 if you don't put it into scientific notation. All right, so when you're calculating heat and it involves a temperature change, you're going to use the Q equation. All right, number 4. They're asking for temperature change, so where would this piece of information go? It looks like we're using the Q equation, and it's aluminum. I will tell you what students often do. They would do, okay, 17.1 grams times 57, and then they'd be looking for a temperature change and not sure what their unknown was. This does not belong here. That is your Q. Okay, you need to look on page 74 to get the specific heat of aluminum, and it is 0.903, so it takes more energy to heat aluminum up than it does gold, times the temperature change, which is what we're looking for. Okay, so 57, look like 5, divided by these two numbers multiplied together will give us our temperature change. Okay, so I'm going to write it over here. 57 divided by, when I multiply those two numbers, I get 15.44 equals our change in temperature. And I got 3.69 is the temperature change. All right. Scrolling. Number 5. I see a chemical reaction. So I'm probably not going to use Q. I see a thermochemical equation is what I see, because I see some heat given off to the side here. And I see by its sign that this is an exothermic reaction because it's negative. So this is one of those where you've got a thermochemical equation, and so it is for this equation as written. So 1 mole of acetone, 1 mole of oxygen, 1 mole of carbon dioxide, 1 mole of water. However, this is not balanced, so let's go ahead and do that because that is important. 3 carbon dioxides, 4 for that. That gives me 6 and 4 is 10 oxygens. I have 1 here, so I need to get 9 out of here, so I could do 9 halves and leave it alone, or I could do this, 2C3, and get to multiply everything by 2 and get rid of the 9 halves. Either way, you'll get the same answer, and honestly, it really doesn't matter for what we're doing here. How much heat is released if I use 155 grams of acetone? Well, this is the amount of heat that is released for 1 mole of acetone. But if I multiply the equation by 2, the heat would have to be multiplied by 2. Okay? So we'll just use it. We'll just use this form of the equation. Okay, so it is negative 790 kilojoules for 1 mole of acetone. How much is it when I convert 155 grams to moles? So 155 divided by the molar mass of acetone, 3 carbons is 36, plus 8 hydrogens, plus an oxygen. Molar mass is 60.08. So 155 divided by 60.08, and I have 2.58 moles times 790 negative, and my amount that I'm searching for here is negative 2,038 kilojoules by solving this direct proportion. So take the amount of heat given in the thermochemical equation, and for any substance in that equation, you can set up a direct proportion and change your amounts. And that is all we are going to talk about in terms of energy in Chem 100. All right, to finish us up today, we're going to just briefly talk about the properties of gases in terms of how we need to think about them, and the concept of pressure, and then we'll start those gas laws at the next lecture. All right, so what we're going to talk about is called the kinetic molecular theory of gases. And it is listed on page 361 in your textbook, which I believe is chapter 11. And it is the properties of gases that are true for what we call ideal gases, which is defined as a gas that obeys the assumptions of the kinetic molecular theory. So I've put in bold here the things that are important to realize about gases. And in general, these properties apply to all gases, but in their absolute truth, they only apply to ideal gases. So we know that gases in general, the particles are very far apart from one another. That's pretty much what makes them gases. They're moving at high speeds, and that keeps them pretty far apart. They're low density, they're compressible, and the reason that they have a low density and they're compressible is that their particles are far apart. When they do collide with one another, now this is not something that happens in reality, but their collisions are said to be elastic, which means that they do not transfer any energy to one another when they collide. So we're being like physicists here in that we are assuming that no energy is transferred. So those are two assumptions. One, the particles are far apart, and that their collisions are elastic. That would also be true in the collision of a gas particle with the side of a container that it was confined to. Because of their fast motion, their elastic collisions, then they are able to overcome any attractive forces between the particles. If they had highly attractive forces, then they wouldn't be gases. And one last assumption of the kinetic molecular theory is that the kinetic energy of the particles is proportional to the temperature of a gas, and this is why we use the Kelvin scale, because it is much closer to that energy, that kinetic energy of the particles. So we always use Kelvin when we're working with gases. All right, so just some assumptions about how gases need to behave in order for the gas laws we're going to talk about in our last two lectures to apply. Unlike solids and liquids, it is not enough to mention the volume of a gas. No matter how small the container is or how large, a gas will diffuse to fill it. Gas volume is also affected by temperature, as you know if you have seen a balloon placed in liquid nitrogen. And another property of gases is the pressure. And all pressure is, and we're going to talk about that in a minute, is the particles of a gas hitting the sides of the container. So the more gas you have, the more collisions you have with the container, and the higher the pressure. The higher the temperature, the more often the particles, because they're moving faster, the more often they collide with the container, so the higher the pressure, and so on. So there are four properties that are needed to fully describe a gas, and that is the volume, and the pressure, and the temperature, and the amount of particles. And in our next lecture, we're going to look at the relationship between those four variables. So volume, and pressure, and temperature, and amount, of course, is going to be expressed in moles. All right, so before we leave the lecture today, let's talk just a little bit about pressure, and we're going to look at some pressure units, and we'll call it a day for lecture 21. Pressure is defined by physicists as a force per unit area, and it's measured in newtons. But there are many other pressure units, and we're going to use some of them today. Of course, the faster gas particles are moving at higher temperatures, the more often they collide with a container or a surface, and the higher the pressure. If you were talking about our atmosphere, then you're talking about something that is composed of many gas particles, and because they hit the surface of the earth, they exert a pressure. Well, the amount of gas particles varies with elevation. We have less particles at higher elevations, and with weather patterns, less inside hurricanes, and so on. So we measure atmospheric pressure, or the collision of those gas particles with the surface of the earth, with many different units, but the original unit was based on columns of mercury. This was done as mercury is quite dense, and you could measure the pressure of the atmosphere with a column filled with mercury that was only 76 centimeters in length. If you used water, which is 14 times less dense, then that same column would have to be over 1,000 centimeters long, or over, let's see, 10 meters in length. So not very practical. So that is why we use mercury, because if it's high density, you can use it to measure differences in pressure. So some different units that we use for pressure are atmospheres of pressure, kilopascals, pounds per square inch. Where is that? PSI, pounds per square inch. Inches of mercury instead of centimeters of mercury. Millimeters of mercury instead of the centimeters. 760 torr. Now what I've given you here in the notes is all the different units, okay? And I'll get back to what standard temperature and pressure are, but this is how they are related to one another. So 1 atmosphere, which pretty much here at sea level we are under 1 atmosphere of pressure, is the same as 760 millimeters of mercury. So when we start doing some pressure conversions, again, your book has tons of problems on this, and it's just the same as, going back and forth between PA for pascals, PSI for pounds per square inch, and so on. So these are many pressure units, and I've given you the relationship between many of them here in the notes. Now, what is standard temperature and pressure? It is defined as 0 degrees Celsius, or 273.15 degrees Kelvin, and 1 atmosphere. So that is what standard temperature and pressure is defined as. So we're going to wrap this up by using some of these pressure relationships and doing a few conversions. All right, so we want to convert each one of these pressures to atmospheres. All right, so using our dimensional analysis powers, we're going to take 921 torr times 1 atmosphere has how many torr, and all we have to do is scroll back up. Let me just, can we do it? No. There we are. Now I probably just lost that. It's not too bad. 1 atmosphere has 760 torr. Okay, so that's how we're going to work each one of these. We're going to take the relationship that's given right up here in the notes, and we're going to just do some conversions. So 921 divided by 760, and that is 1.21 atmospheres, A. So I'll put the answers up here. Okay. All right, so for pascals, there's how many pascals are in an atmosphere. So 4.8 times 10 to the 4th pascals times 1 atmosphere, which is what we want, so it's on top, has 101,325 pascals. Now, I think one of your recitation problems asks for kilopascals, so you could add it to here. It'd be 101.325 kilopascals in an atmosphere. Anyway, back to this. So that would be 0.474 atmospheres. Okay. PSI, 87.5 PSI times 1 atmosphere has, it's right here, 14.7 PSI. So 5.95 atmospheres. C. And then D, 34.22 inches of mercury times 1 atmosphere has 29.92 inches of mercury. And I come out with 1.14 atmospheres. So some pressure conversions and some properties of gases so that we can apply the relationships between pressure, volume, temperature, and amount in these simple gas laws in the next lecture.